Good afternoon, everybody. It's time for the webinar to start now, so we'll give it one more minute and just give everybody the chance to join. So I'll be back in a minute. So, hello, good afternoon, everybody. There's a lot of people joining us from across the world today, so that's fantastic. Welcome to the second webinar that we are running. It will be a series of many. This webinar will be recorded, so you will receive an on-demand link for this webinar after the event. Now, just to let you know that the webinar link might be a little bit delayed because of Cisco dealing with all the on-demand links that they have to produce. So just bear with us, but you definitely will receive the on-demand link. Just please note to make sure that you are on mute to give our presenters a chance and everybody can hear him clearly. So I'm Cornell Roberts, the Marketing Manager for YIC Technologies, and I'm delighted to welcome you all to this webinar. I would like to introduce to you Professor Arturo Mediano, who's from the HF Magic Lab at the University of Zaragoza, and he's YIC's collaborator, and he will be leading today's presentation. Professor Arturo is the founder of the HF Magic Lab, which is a specialized laboratory for design, diagnostic, and troubleshooting of the EMC and EMI fields. If you have any questions during this webinar, please use the chat function, which you will find at the bottom of your screen, and we will aim to answer each question after Professor Arturo's presentation. So many thanks for participating in this webinar. Enjoy it. And I'll hand over to Professor Arturo now. Thank you very much. Bye.
Hello, everybody. So thank you, Cornell, for your nice presentation, and welcome to everybody to this webinar about near-field scanners and near-field tools. What I am going to try is to review in a little more than 1 hour some of the ideas related with how to make debugging of the electronic circuits with in the near field. When we are interested, especially finding where we have a specific area that is aggressive and, for example, is creating failures in radiated emissions. Okay, to make the presentation, I'm going to share my screen. So let's open my screen here, and I hope you will be able to see it in a moment. Okay, so if there is no problem, now you have in your screen the first slide of my presentation. This is what we are going to do: is EMI, EMC Design and Troubleshooting using near-field probes and scanners. As Cornell was explaining, my name is Arturo Mediano, and I am from Spain. So first, let me give you a big whiz related with the solution of the coronavirus in your country, in my country, and in the world in general. Well, this seminar is organized by YIC Technologies. It's a company that is collaborating with me from some time ago, and is the company that is presenting the scanners that we'll be using in my demos. Like Cornell was explained, my laboratory is called the HF Magic Lab. We are in Spain, in Zaragoza, and we are specialized in solving and analyzing problems related with high frequency, like, for example, EMI, EMC, signal integrity, and because this topic is not very easy for some companies, especially companies working in low frequencies, not familiar with antennas, with wireless communications, or with radio frequency in general. That is because the name of the laboratory is the Magic Lab. Well, let's start with the outline for the session. The first part of the seminar will be related with the theory, not with equations, only the fundamentals for near field analysis. Then we will have some demos. Let me show you the setup. So this is the setup I will be using in my demos. You can see here the instruments I will be using, the scope, the power supply. I will be using the flat scanner. This scanner has around 1,200 small near field probes for measuring especially PCB circuits, and I will be using the EM probe, that is a scanner that is using only one probe that is running around some specific circuit to find aggressive areas like this. This is for the second part of the seminar. So in the first part, I will be trying to explain these ideas. Basically, what is EMI and EMC culprits and victims. We will be presenting ideas for example, what is electric and magnetic field and wave impedance. We will be talking about near and far fields. And when we have clear this area, we will be able to go to the demos, where I will be doing some demos with near field probes, handy near field probes, with the scanners. And I will be doing experiments to demonstrate what is the spectral scan, the spatial scan, and many other features of this kind of tools. No? At the end, we have the conclusions and the time for questions. You can ask what you want. If I am able to answer, I will be glad to do this. And if I don't know to do that, I will try to give you the opportunity to receive the response later by email. Well, this is the first slide to introduce the idea. No, we are worried about EMI. What is EMI or EMC? It's a problem for many electronic manufacturers that experiment this problem. The idea of that some kind of transmitter of electromagnetic energy send the signal to some kind of victim. Usually, the victims are circuits working with very small voltages, currents, or in general signals. That is because typically a good EMI receiver is a radio or a TV receiver. But really any kind of electronic product can fail with electromagnetic energy. Medical products, home appliances, audio systems. And basically, the transmitter can be some kind of intentional transmitter, for example, a telephone, a walkie-talkie, or some kind of radio or TV transmitter, or, for example, can be some kind of unintentional transmitter. I mean, for example, the power supply of your computer, the motor that you have in some kind of a home appliance at your home, any kind of electronic circuit today can create these kind of problems. These problems have three important parameters to control. One parameter is the distance. When you have a short distance between the culprit and the victim, you have more probabilities to have problems. Another important parameter is the frequency. Typically, we will find more problems if we work at higher frequencies. Obviously, you can find problems at 50 or 60 hertz, especially magnetic field problems many times. But if you increase the frequency of your system, probably you will be more aggressive and you will be more sensitive to the environment. And finally, power. Systems with big signals in amplitude or with small signals in amplitude are more typically aggressors or victims for these kind of effects. Well, in EMI and EMC, we consider two different problems. We talk about emission problems, or we talk about immunity or susceptibility problems. When we have emission problems, that means that your product, an electronic circuit, is creating radiated emissions. I mean, electromagnetic energy goes to the air and is able to arrive at some distance to another electronic circuit. Or you can inject the signal, this EMI, can be injected in the power supply cord, in the power supply system, no? For example, the 120 volts, 60 hertz, if you are powering from the mains, or for example, the DC voltage, if you are powering a system in an automotive application. In the opposite point of view, when you are interested in immunity, the idea is that your product can receive energy through the power supply cable and then this power supply cable can carry energy that can create a failure in your product, or you can receive the energy through the air, and this is what we call radiated EMI in immunity point of view. Both emissions and immunity are limited by regulations. You cannot sell a product without comply this kind of regulatory limits. That is because it's familiar for you, I am sure. Yes?
I'm sorry. I think we still see your lab in the background. Are you sharing something on the other screen?
Yes, I am sharing the slides. Sorry, let me see what happened.
No, so we don't see that.
Okay, let me see why this happens. Okay, let me see.
All we see is the lab, actually.
Yeah, I understand. Let me try now. Where is the screen of?
Okay, now we can see the slide as well.
You see the slide now?
Yes.
Oh, but this is not the screen I am sharing. Okay, that I don't know why. Okay, sorry. Let's go. You see now the screen, the slide?
I can see the slide. Yes.
Okay, sorry. Let's go to the back. This is the slide I was explaining before. No, when you have a problem of EMI and EMC, the idea is that you have two different problems: emissions, or you can have immunity and susceptibility problems. I was explaining that your product can inject noise in the environment through the air. This is what we call radiated emissions, or we can inject the noise in the power supply cord in this direction. So this is what we call conducted emissions. If we are interested in immunity or susceptibility, the idea is that the noise is received through the air or is received through the power supply cord. Now, both problems are limited by regulations. So let me see what happens if you are interested, for example, in a problem related with emissions. No? This is a typical plot. This is a typical result where you are failing in radiated emissions. In yellow color, you can see the electric field. You have some distance, typically 3 meters, and in red color, you have the limit of regulations. You can see that in this example, in this area, in these frequencies here, this area here, we are failing at close to 10 dBs over the limit. This is a response that is in some kind of mountain, is what we call a broadband emission. Broadband emissions, because the energy is below this mountain, and because of the resolution bandwidth of the spectrum analyzer or the EMI receiver we are using, we are not able to identify specifically at what frequencies below this mountain we have the emissions. This is fully different to a narrowband emissions, like this one. This is the typical result from the emissions when you have a clock that is creating radiated emissions, for example, with the harmonics of 20, 30, 50 megahertz clock. No, you can identify clearly with these lines at what frequencies you have energy, at what frequencies you don't have energy. One of the main problems that a designer has is to find where and is created this energy, and basically where is the path of this energy from the source to the victim. And here is where the near-field probes can be useful, scanning your prototypes or your designs in the test session. Well, let's explain some idea in a non-very formal or academic point of view related with what is the points of view you have to analyze a circuit. For example, you can consider to analyze the circuit in the circuit theory point of view. This is what we call Kirchhoff. No? So you have this electronic circuit, you start to consider that you have voltages between different points in your circuit, and you have currents, and these currents are going through the traces. So many people, when designing a circuit, this component, and they are connected to ground, this is the connection. They plot things like, for example, this voltage, and they plot the current like something that is going inside of this wire, inside of this trace. No? But the idea is that with this point of view, we are not able to understand many of our EMI problems. Obviously, it's a point of view that is very useful, because if you multiply voltage and current, you have power, or if you calculate the ratio between the voltage and current, you have impedance. So typically, when we are designing circuits, we work with voltage and current, or we work with power and impedance. It depends on what is more practical for my specific application. But sometimes we need to analyze the circuit from the electromagnetic point of view. That means Maxwell theory. No? So for example, consider that electric field is something that I draw in red color. Electric field in my circuit is something like this around the components, around the traces. Remember, in electromagnetic theory, the energy is not inside of the wire, inside of the traces, around the components. That is because you can plot clearly this electric field like some kind of fog around your circuit. And if we plot in green color, for example, where is the magnetic field, something like this, is something similar. We have magnetic field, and this magnetic field is like fog around my components. We have two different circuits in our designs. Perhaps we have circuits with high impedance, or perhaps we have circuits with with low impedance. So in electromagnetic theory, we can do a similar calculation to the circuit theory. We can multiply electric and magnetic fields, so we obtain the Poynting vector. This is related with the energy of the signal, and we can calculate the ratio. This is the units of electric field and magnetic field. This ratio are ohms, so this is what we call wave impedance. Typically, we try to consider that electric field are related with voltage in the other point of view, and magnetic field is related with current in the other point of view. So you have a system with a high impedance. That means you have more voltage than current. So this is equivalent to have a high impedance circuit in electromagnetic theory. That means high impedance is a high electric field and low magnetic field. And the opposite if you try to think in low impedance point of view. Well, where is this energy? Remember, this energy is around the component. It's around the conductors. This energy is not far from the circuit, but you have the possibility to experiment this effect. A part of this energy, perhaps a small part of this energy, is able to go away. This is what we call radiation. This radiation, this radiated energy, needs some specific element in your system. You need to have in your system some kind of antenna. So for example, if you are designing a wireless system, you will prepare some small PCB trace or some small wire to be able to radiate 2.4 gigahertz, because this is the signal that you want to radiate or to pick up from the environment. But when you are designing an electronic circuit, you can create a lot of unintentional antennas. And if these unintentional antennas are excited with the harmonics of your clock, with the harmonics of your signals, with the frequencies that are involved in your design, you will be able to have energy at some specific distance. This specific distance is what we call the far field. So it's very important to make a difference between the far field, what we can consider that is here, and the near field, that is something that is close to the circuit. The close or the far concept is related with the frequency of the signal, and this is what we can plot here. No? We are going to plot how much is the wave impedance. Remember, wave impedance here, the wave impedance is the ratio between the electric and the magnetic field. And consider that this is the circuit that is creating the signal that is being radiated at some distance. When you are far from the system, when you are, for example, here, at this point, you are here, okay, you receive something that in circuit theory, in electromagnetic theory books is explained like a plane wave. So in these books, they explain that you are receiving electric and magnetic fields that are perpendicular. No, this is what in these books is explained like a plane wave. So if you are at this distance and you measure electric field and you measure magnetic field and you calculate the ratio, this ratio is basically related with the ratio between the permeability and the permittivity of the air, of the media. It's not dependent of the nature of the circuit that created the signal. It's only a property of the media. And if you calculate this ratio, you will see that this ratio is exactly 377 ohms. This is 377 ohms. So what happened at this point? At this point, you have a wave impedance that is 377 ohms. If you go to this point and you make the same calculation, you will see that the value is exactly the same. At this point, the ratio is exactly the same value. So in this area, the wave impedance is exactly 377 ohms, because if you go away from the circuit, if you go in this direction, electric and magnetic field are attenuated in the same proportion. So the ratio is constant. Is this 377 ohm? And remember, this ratio is independent of what kind of circuit was creating the signal. We have, for example, in the limit, two different circuits that can create these signals. Consider circuits with a low impedance or circuits with a high impedance. What is a circuit with low impedance? With circuit with low impedance, for example, is a loop. We have current and you have a small voltage. And what is a circuit with a high impedance? For example, consider a monopole. It's a circuit with a wire that is open at one end, at here, and then you are exciting with a voltage. This is a circuit where you will have, close to the circuit, basically electric field. So if you are measuring electric field, and at the same time that you are measuring electric and magnetic field, you go close to the source of the signal, you will see that the wave impedance at some distance start to decrease, or the wave impedance start to increase. When the impedance increase? The impedance increase when the origin of the signal was some kind of high impedance circuit, like I am representing this high impedance circuit with an open wire, monopole. And if you go down in the wave impedance, it's because the origin of the signal was some kind of low impedance circuit, like, for example, a loop. This is what I am trying to represent here. So what happens if you are measuring signals in your EMI debugging activities? You have three areas where you will be measuring. You will be measuring in the area number 1. In this area is where we are in the far field. The area number 2, this is what we call near field. And inside of the near field, we have the possibility to be interested in big electric field and small magnetic fields, or big magnetic fields and small electric fields. So you will need three different elements to do these measurements. The first element you need in the far field is one antenna. This is the area where we use antennas. This is the area in the near field. This is the area where we use near field electric probes. And this is the area where we use near field magnetic probes. So we need the three different probes to make the measurements depending on the area where I am. The output of these probes, the antennas, near field electric probes or near field magnetic probes, can be connected to your instrument of interest. Some kind of, for example, a spectrum analyzer, some kind of oscilloscope, some kind of meter, EMI receiver, and you will be able to see the frequency or the time domain point of view of this signal. And where is the distance between the near and the far field? That this is something that many people is interested in. If you try to go to electromagnetic theory, this is a known, very easy task to calculate. But in EMI debugging, we consider that the distance where we can go from the near to the far field is basically lambda over 6. So you need to calculate how much is the lambda, the size of your signal, to know what is the distance between the near and the far field. One example, if your frequency is 300 megahertz, you will see that lambda is 300 over 300 is equal to 1 meter. So lambda over 6 is equal to 100 centimeters divided by 6. This is something like, I don't know, more or less 15 centimeters. If you are close to the circuit at, I don't know, 5 centimeters, you are in the near field. If you are at 1 meter, you are in the far field. when we are measuring electromagnetic compatibility, typically we are measuring at a minimum frequency of 30 megahertz. And typically, the shortest distance is 3 meters. If you do this calculation, you will see that 3 meters for 30 megahertz is the far field. In the laboratory, in the semi-anechoic chamber, you are always measuring in the far field. But if you are failing in the far field, it's because in the near field, you have this energy. And this energy is being radiated by your antenna. So it's very useful to go to the near field and to find where is the origin of this signal that is in the far field over some kind of limit. No? And this is what we try to do with near field systems. With near field systems, we will be interested in working in this area here to understand how is the circuit we are designing. So what is a near field probe? Very easy to understand. We need two different near field probes, electric and magnetic. Let me prepare a homebrew near field probe. You take a piece of coax cable, you remove a small part of the shield, I don't know, 5 millimeters, 3 millimeters of the inner conductor out of the shield. This is a near field probe. You only need some kind of, I don't know, isolation material. This is typically around a probe. So if you are scanning around the circuit, you will not be creating some kind of short circuit. But in this small element, you will be receiving the electric field lines that you have close to the point where you are locating the probe. This is a very small probe. You will be receiving a small quantity of electric field lines, and the output of this probe will be very small. But the advantage of this probe is that this probe is very good for spatial resolution. You will be able to identify that the emissions came from one specific pin in one integrated circuit. If you are interested in scanning a big board and you want to find where is the area that is creating the problem, it's better to go to a bigger probe. Usually, a commercial bigger probe, the inner conductor here includes some kind of bowl or some kind of metal plate, so you can pick up more electric field lines. And with these electric field lines, you are able to identify the area where the system is creating the energy. No? I mean, for example, you can use the big probe to scan the full PC board. You identify that the problem is on top of the DC-DC converter, and with a small probe, you can scan to find that the problem came from, is especially on top of the diode of the buck converter. And this is a very, very effective tool to find problems. In a magnetic field probe, what you need to create is a loop. So you take a piece of wire, and you connect the piece of wire directly to the shield. You are creating a short circuit. You are creating a loop. And then any kind of magnetic field line that goes from the environment is received by this loop and is going to the output of the probe like a voltage that you see in the instrument. Remember, this kind of loop is sensitive basically to magnetic field because it's a low impedance system, but you can have some kind of electric field sensitivity. That is because in commercial probes, sometimes this loop is prepared in this way. They make the loop, but then they extend the shield of the coax cable in this way. So this is the shield that is going around the inner conductor, and then they create here a gap. Sometimes the gap, instead of being here, sometimes they put the gap in the middle of the loop, because in this way the probe is symmetrical. What is this? This is a magnetic field probe that is shielded for electric fields. So for many, many debugging applications, this kind of probe with a loop is very, very effective. But sometimes it's very useful to have this shielding effect. This is what you will find in commercial probes. I am using in this picture the probe, for example, for scanning a PCB. I can scan some kind of cable, the activity of a cable, or I can try to find in an enclosure if I have leakage around the cover or around some kind of connector. Many people know that the near field probes can be used for finding hot areas in your design. But near-field probes are very useful too for immunity. In this immunity point of view, what you do is to inject signal in your near-field probe. So you inject signal from a signal generator with a small power amplifier. I don't know, 1 watt, 2 watts, 3 watts. You don't need a lot of power. You inject the signal in the probe, and then you will be exciting specific areas of your circuit. In this way, you can find what areas of your circuit are sensitive to some specific frequency and some specific modulation shape, okay? But we are interested here basically in emissions. What is a near-field scanner? Here, I have only one probe, one loop. Here, in one scanner, I have 1,200 small probes that are in a flat surface. So you can put on top of the scanner your circuit, and these probes measure how are the emissions from the circuit, switching the output of any of these probes very fast electronically. This is one of the possibilities. So in this way, what you have in your laboratory to be able to measure in this way, what you need is the surface with the probes. You need a spectrum analyzer. For example, typical spectrum analyzer from Rod & Schwartz, from Keysight. This kind of good instruments are compatible with this kind of scanners. You need a software that is offered by the manufacturer of the scanner, and a small adapter unit, okay? Some models of scanners introduce a spectrum analyzer inside of the scanner, but at this moment I am going to consider this idea. With this kind of scanners, we are able to scan, for example, between 50 kilohertz, no, I think this is wrong. I think it's around 100 kilohertz, up to 8 gigahertz. We have here 1,200 small probes with a resolution that is around 7 millimeters, 5-7 millimeters. If you want the details of the product, please ask the Joran from YIC, because I am not expert in the details, okay? And the other possibility that you can work is with only one probe. The idea of this scanner, that you have this idea in the market, is this kind of probe, one probe that is in the arm of a robot. And then the robot can scan a PCB board at different heights, no? Instead of this flat surface, like I was explaining here, no? The disadvantage of this system can be, for example, the speed, no? This is not a real disadvantage for many of the debugging areas, like I will explain later, but this is the disadvantage compared with the flat scanner. At the same time, the flat scanner is faster, no? Because the switch of position is electronic. And what can you do with this kind of scanners? Basically, you can do two things. The first thing you can do is one spectral scan. That means you are able to scan from one frequency to other frequency what signals are close to your circuit. This is one of the most important and interesting ideas to receive from the, or information to receive from the scanner. The other important thing you can do with this kind of scanner is one spatial scan. For these frequencies, or for any specific frequency, you can create this kind of plots where you are able to identify that specific frequency that is of interest for you, where is located in your layout, where is located in your cables, where is located in your enclosure. And then you can apply fixes, capacitors, farads, some change in the software, and then you will be able to try to solve the problem. Then the main advantages of this kind of analysis that you are able to identify, for example, critical loops, you can find the source of emissions, or for example, you can understand why the product is failing. This is very important to avoid the trial and error process that many times we use when debugging an EMI problem. We can learn for the future, and you can do this, for example, for layouts in PCBs, cables, and shieldings. This is a very useful tool, and I like a lot, especially when I am teaching, because when you can see things, it's easier to understand. Oh, this is a sentence that I explain to my students many times. If you can see it, you can fix it. Okay, so this is what I am going to do in this webinar, is to show you with some examples how these instruments can work. So let me disconnect this screen. So now I'm going to go back to this area. Now this is my camera. I hope you, if not, let me know, Yoram. I suppose now you are looking at a green area in the screen with my hand. And then we can see here the first idea. The first idea is to explain the near-field probe. This is a commercial near-field probe. You can see that this is a small loop here. Or, for example, you can find this kind of kits. You can open the kit and you will find different probes. One probe can be bigger or can be smaller. And you can find that these probes are for example, in this case, is for H-field loop, is from 0.3 to 100 megahertz. Or, for example, the other probe is an electric near-field probe that goes from 20 megahertz up to 1 gigahertz. No? So usually what we have in our laboratory is some kind of kit of probes. This is another typical kit that you can use for debugging. Okay, like this one, you have several probes, and you connect these probes with a coax cable to your instrument. This is what I am going to do in my first example. In my first example, let me show you the PC board I will be using. Is this one. This is a small PC board where you can see I have displays, I have a microcontroller, I have several drivers for the LEDs, I have a real-time clock, I have a crystal for the microcontroller, several keys, I have, I don't know, different elements in a 2 layers board. This is the top layer, and this is the bottom layer, is the second layer. There is no ground plane. This is a layout that is done with a system that is working without problems, and I am powering the system from these 2 points from 5 volts. So I am going to apply here 5 volts. Let's take the circuit here this way. Let's take the voltage in this way. Okay. And let me switch on my power supply here. Okay. Yep. Okay. The system now is working. I can touch the keys. And then consider I am interested in measuring how are the emissions. No? But I am going to measure the emissions. Let me try to use the other camera. Is to show you the screen of my instrument. No? So this is the instrument I am going to use. So I'm going to take the oscilloscope and I'm going to connect the near-field probe to channel number 1. So you will see in the screen of your computer this screen of the instrument in a better way. No? This is the screen of my scope. And let me connect the near-field probe to the scope. No? Let me try to do this for you so you can see both things at the same time. Let me reduce the size of this. Let me reduce the size of this. Okay, this way. And this is the screen of the scope. No? So when I connect with a coax cable, let me connect to channel number 1. And let me connect in this way with the adapter. I have an adapter here. I connect the near-field probe. Then, when I go close to the circuit, I am able to identify where I have activity. Remember that in a PCB, currents are in some kind of horizontal plane. So the magnetic field, let me change the size of the system this way. Okay, so if currents are horizontal in the PCB, the magnetic field is going vertical. So if you put the probe vertical, you will not be able to pick up as much energy like if you put the probe horizontal. No? So for example, when I go in this area, I detect more energy. When I go here, I detect more energy. When I am on top of the microcontroller, I have more energy. Obviously, this is the time domain signal. No? Of course, in EMI, many times, additionally to the time domain signal, it's very useful to see the frequency domain. No? This is the energy I am taking from the probe. Let me take the FFT up to, for example, 500 megahertz. And let me change the resolution bandwidth to 100 kilohertz. And then you can see that I can identify exactly when I am far from the circuit. Then when I go here, I can identify the areas where I have more or less energy. You can go to find specifically some signal, and then you can do some kind of changes in your circuit or in your software to reduce or to kill some specific frequency. So this is only to introduce you the idea of a near-field probe. I use near-field probes every day in many of my analysis. But let's go to the idea of using one scanner, okay? So instead of scanning the board in this way, I'm going to switch to another camera, okay? So you can see here, this camera. Let me switch on some lights so perhaps you can see better the surface, okay? And let me put the scanner, the PCB on top of the scanner. Look at this. I am going to put in this way. I'm going to put here the PCB, okay? The PCB is more or less fixed because I use this kind of blue tack elements, no? They are very handy, very useful to be able to put on top of the scanner. So I am going to put here the PCB, and I'm going to put here the power supply cable, no? Then I am able to open, let me see, okay, compartir, wait, I'm sharing this screen. I don't know why. I want to share. Now I'm going to change here. And now let me open the software. Joram, in theory, now we are with the software of EMViewer on. So I hope all of you see the software. Okay, let me see. Here it is. Here, okay. Okay. This way. You see the software? Joram? Please?
Yeah.
Okay. Okay. Thank you. Thank you. It's only to avoid problems. Okay. So let me switch the orientation of the camera so you can see the PCB like I see the board. And let me explain how we work with this. First, I'm going to create, this is the software of the instrument. I can select any of those scanners. If you go here, I can select the EM probe, or I can select the EM scanner. The EM scanner is the surface. So let me set the scanner, and then you need to connect the radio frequency output of the scanner to the spectrum analyzer. Let me check that it's connected, correct. And then, when you have connected the EM scanner to the spectrum analyzer, you can create some kind of specific nodes. You can create a spectral, spatial, spectral comparison, spatial analysis. Let me go to a spectral. And in a spectral, the software gives you the possibility to specify what kind of frequency range. For example, let me consider I am interested in the range from 10 to 120 megahertz. Let me put the resolution bandwidth in 120 kilohertz. Let me establish measure peaks. Measure peaks is that I am going to select the 4 of the biggest peaks in my analysis. And for intermittent signals, sometimes it's useful to specify the peak hold, this square. If you select this square, then for random signals, when you are doing a continuous scan, you will be able to pick up this kind of non-continuous or intermittent signals. No? Then I select the probes in the scanner that are of interest for me. For example, let me select known now. So my product is now in this area of the PCB. No, if I change the camera, you will be able to see that basically. Oh, sorry, I have touched the color. Okay. Now and now. Okay. Now you can see basically that the circuit is between the columns P to AF and from 6 to 16. So you go from P to AF and from 6 to 16, and you select cells. This is very useful because in this way, you are not scanning the full area because I am only interested in this area. For a spectral scan, it's not necessary to select all these areas. I can select better some of the points that are in this area, because then the scanner will be faster, the scan will be faster, and I will be able to pick up the energy in the same way. So I'm not going to change other of the possibilities of the system. And then the first thing to do is to make a measurement that is with the device under test off. So I'm going to power off my circuit. The circuit is now without power supply. And then I run the scan. When I run the scan, the software configure the spectrum analyzer, make the scanning of the PC board, and then I will obtain here the results of the scanning. No? You can see that from 10 megahertz to 120 megahertz, I have only activity in this area, that is the area of FM broadcasting, with this kind of levels. No? Later we will see what these kind of levels are. Obviously, if you make these measurements in some kind of a shielded structure, you will have more possibilities to reduce this noise from the environment. And look at this, the system is measuring the biggest peaks, no, 4 in this case. No? Now, let me switch on my device. I switch on the device, okay? I can put some numbers. Later, the numbers will disappear because in the software is specified in this way. And I'm going to repeat the scanning. No? So I can do one scan, or I can scan continuously. Later, we will do the continuous scan. No? So you can see here the difference. No? This is with the device under test off. This is with the device under test on. Obviously, I can use the same scale. No? So let's see how is the scale for the situation with the switch on. This auto scale is going from minus, for example, minus 3 to, for example, 19. This is the scale for the device on, minus 3 to 19. So I go to the other measurement, and I'm going to specify the same scale, no? Minus 3 to 19. In this way, it's very easy to compare how is the difference between one and the other. I can create some specific node that is called the spectral comparison. In the spectral comparison, I have another net that is waiting for the specification of the measurement, some kind of reference, and then I will be able to see the comparison. No? For example, as the reference, let me select from my spectral analysis the noise in the environment. So I put it here. This is the noise from the environment. Now, from the test point of view, I'm going to select the device under test on. So this is the device under test on. This is the ambient noise. This is the comparison. So you can see that specifically these frequencies are created by my circuit. You can see that I have some specific frequency. For example, I am interested in this, or I am interested in this. If you go to the previous, let me close the comparison, you can see that I have here one peak, the second peak, the third peak, the last peak here. This is the biggest peaks in my circuit. No? The idea is, for example, if you are interested in this peak, where is this peak in your circuit? This peak is around 11.06 megahertz, 11.06 megahertz. So let's go to the spectral scan, and let's go to the add nodes option, and then a spatial option. What is this? This is I am able to do now a spatial scan, but based in the previous spectral scan. So I am able to specify at what frequency I want the spatial scan, or I can go to the peak marker list where I have the frequencies that have been measured by the system. No? In this case, for example, the 11.06 megahertz. I am going to use the 120 kilohertz resolution bandwidth, and let's go to the spatial scan probes. Now it's different, because I am not interested what frequencies I have in this area with some specific amplitude, but I am interested in where is specifically in my PCB. So really, I need to select all the cells in my scanner. Then I can put the other options of the software by default. It's not a problem now for my demo. So I can go here, and you can see what happens if I make a run of the scan, okay? So I go to the setting of the spectrum analyzer. Now we do the scanning, okay? The scan is complete. So you can see here that I have here how is the activity in my PCB. I can make a zoom here, so it's easier for me to understand, no? So if you move the pointer, you will see that with the mouse, the pointer is only specifying that the frequency is 11.06 megahertz. Why? Because this is the frequency I am interested in. Later, I will show you that you can do a spectral spatial scan, and this is very useful to identify several frequencies in a full system, no? The idea is, but this area, where is? The area is if I see here the PCB, it's clear that the area is around the microcontroller, and it's around this area, and it's going in this area, but you can see that this color is yellow. I have some kind of activity in this area. So that is because in this PCB, this line that you see here is basically the ground. The ground is not in a ground plane. The ground are traces that are far from the forward lines. So we are creating big loops. So let me see if I am able to locate exactly where is the activity. I can go here, and I can edit the overlay. What means the overlay? I can import here some kind of, for example, picture. Let's go, no, some kind of Gerber file. Let me see where is here, the overlays. And let me go to the overlay of my, the Gerber file, sorry, here. It's a file that is the silk screen of the design. So I can rotate clockwise, and then let me mirror vertically, and then I can put, no, sorry, is rotate clockwise. Now it's correct. So I can put the silk screen here. Okay, apply, and okay. So now it's easier, sorry. Now it's easier for me to see exactly, okay, to see exactly where is the activity. You can see that here is the microcontroller. The activity goes from the VCC pin to the ground pin. This is a microcontroller from Philips, and the VCC pin is this pin, and the ground pin is this one. So it's going, the activity is going in this direction, and it's creating this loop in this area. But obviously, I have some kind of return current in this way at 11.6 megahertz. Why is this? Let me show you the camera. Okay, if we go with the camera to make a zoom, if we make a zoom with the camera, okay, not easy to do. Let me go here. We go close to the circuit. Okay, you will see the crystal here. Okay. The crystal here is 11.0592 megahertz. So this is obviously a very simple example, and it's very easy to know for people with experience in electronics that when you see these harmonics are created by, they are related with the clock of the digital system you are analyzing. So really what I have here is a big loop, no? Let me show you what happened if I introduce in this circuit. Let me open here. Where is the circuit? Here. Here. Where is it's appear? Where is the spatial scan? What happened here? Where is, I have removed the, where is the image? Sorry, I don't see where is, where is, what screen? I have several screens in my computer where I don't know where is the screen. Okay. Open here. Is here, here, and this is appearing. I don't know why. Oh, let me scan again. Okay. It's here. No, it's here. No, I don't see where is the screen, sorry. Okay, so let's go here. It's disappeared. Ah, now here. Sorry. Okay, so now this is the previous one. Okay, was hidden. My screen was minimized. No, so let me see. This is let me remove the last one. And now you can see that this is the result. But now this circuit, the decoupling capacitor is here. The decoupling capacitor is close to the pin, ground pin, and it's not close. It's not in with a very small loop. No. So let me introduce now how is the effect of this decoupling capacitor. No. So let me introduce the decoupling capacitor. It's a 100 nanofarad capacitor. Okay. So you can see in the camera how I am introducing the decoupling capacitor. Okay, this way. This is the capacitor I am introducing. And let me run again. Okay. Let me run again. You can see. Okay. And let me edit the overlay again. Let me mirror vertically. And let me rotate clockwise. Now let me put here. So apply. Okay. So we can see the difference. Now to see the difference, I need to use the same scale. So let me go here. Let me go here, and let me see what scale I am using in the first result without the decoupling capacitor. Let me put here -3 to 31, -3 to 31, and I go to the second measurement, and let me put here -3 to 31. If not, if we have selected the auto scale, we will not be able to identify clearly the difference. No, you can see this is without the decoupling capacitor. This is without the decoupling capacitor, and this is with the decoupling capacitor. We can see automatically how is the difference between them. No. Let me consider what happens if I add some additional element in my design. Consider, for example, that my PCB is powered with a DC-DC converter, not a linear power supply. I'm going to change my power supply with a DC-DC converter. Let me change this one. So you can see here. Up. Okay, this way. Okay. And this is my small DC-DC converter. I have really here two DC-DC converters. One is a 12 volts and the other is a 5 volts DC-DC converter. I remove from here the 5 volts cable, and let me replace with a shorter cable, this one. Let me introduce in the board now. And now I am going to take the output from the back converter. No? So the idea this is consider that, for example, this is your design. You have a big PC board, or you have several PC boards. This is the power supply board. This is the microcontroller board, and there is a small cable that is connecting with the power supply. No, let me put the cable exactly on top of the of this orange line of cells, so it's easier to identify. And this is the DC-DC converter. No, now the DC-DC converter will take from my power supply a 9 volts voltage that is going to the pins of the PC board. Okay, this pin and this pin. No, now this is 9 volts. This is the back converter with the inductor of the back converter. This is the cable carrying 5 volts that goes to the microcontroller board. No? Obviously, to make a scan of this system, I need to do some kind of additional setup. No, I need to change the probes. Let me make a note that is different. Let me make a spectral spatial analysis. No, and in the spectral spatial analysis, I select the frequency range again. For example, 100 to 120 megahertz, 120 kilohertz. Let me not select the measure of peaks. So in this way, the scan is faster. We select the spectral spatial scans known here. Let me scan in this area, more or less. And now I need to introduce the area that is close to 10 to this area here. And let me scan the area where we have the cable. Okay, this is the spectral spatial scan. No, sorry. In the spectral spatial scans, I need to specify all the probes for both analyses. Sorry, there is no one spectral, one spatial. It's both of them. So I need to make this analysis for these probes, select. Then I need to specify from 10 to, for example, the 19. This one, 1920. This is the area where I have the DC-DC converter, and this is the area where, this is the area where I have the cable, more or less. Okay. So this is the cable, this is the DC-DC converter, and this is the power supply. No, and let me introduce some kind of overlay. In the overlay, instead of this one, let me import a picture. You can import a picture of the PCB or of the PCBs. No. So I can put here the PCB, and I can adjust as best as possible. Obviously, I have prepared these pictures, so but it's not very difficult, no? But in this way, we don't need a lot of time to prepare the setup for the demo for the webinar. Okay, more or less is the area. Oh, I need to move my scan. My PC board. Okay, sorry. Let's go to this. It's 11 this way from here. Okay, and then we need to put this. Okay, this way. I'm scanning this area. Okay, so in theory now it's better. No. See, yes. Now it's correct. No, now I have. No. In the picture, this back converter is exactly on top of the orange color. No, so this is the cells here. You can see that the cells, the orange row is on top of the back converter PC board. That is the same here. No, so this is okay. And then here I need to remove these lines here and select. Not necessary really, but in this way perhaps we will have a faster scan. No? So I have here the picture, accept, and then I can run the analysis. So now the system will be scanning for the full number of cells in the full frequency range. In this case, from 10 megahertz to 120 megahertz with a 125 kilohertz bandwidth. You can see how the scanner is doing the scan. Perhaps the picture will not be exactly in the millimeter with the position of the components, but is enough to demonstrate the utility of this. Okay, so you can see that the scanner is not doing a big scan. Okay, you can see that close to the cable we start to have activity. Why? Because in the cable we have energy that is going, especially in common mode. We have two wires. The activity in differential mode is not creating big activity in the environment because the cancellation effect, there is no loop, but the noise that is coming from the DC-DC converter that is injected or is exciting the cable in common mode is one of the most typical problems that I have found in commercial products when failing in radiated emissions. No? We are close to finish. Sorry. I go some fast, so we are on time. So we have here the result. We can see that nothing happens. Okay, this is the environment. Sorry. Let me switch on the power supply. Let me switch on now the power supply. So oops. Here, let me switch run again because the power supply was off. Sorry. Okay. System is scanning again. Okay. We can create additionally to this kind of nodes, spectral, spatial, spectral, spatial. we can compare spectral analysis and we can compare spatial analysis to make measurements in both domains. Okay. Now we can start to see more activity, obviously. We can see the harmonics. This is the harmonics that are coming from the microcontroller system, and we start to see the broadband activity that is coming from the DC-DC converter, no? Remember that from the DC-DC converter is switching, I don't know, at 100 kilohertz, 200 kilohertz, but it's very typical to obtain from this kind of converters EMI that can create failures in radiated emissions between 50 megahertz up to 200 megahertz, for example. This activity is coming typically from ringing in the switching activity of the transistor or the diode, or from some kind of parasitic oscillation that you have created in the layout of your PCB. This kind of analysis is very useful to identify exactly where you have these problems, no? So now we are finishing here the scan of the PC board, the main PC board, and now we are going to finish the DC-DC converter. Let's make a zoom of the system. Okay, it's finished. We are going to make a zoom here. We can remove the picture, so you can see that now we have all the activity in the PCB, and when I move the mouse around the system, both amplitude and frequency change. So look at this. This is a green color, but if I am with the mouse on top of the green color, I can identify that some frequencies are 11 megahertz, other frequencies are 33, and some frequencies are 55, because it's the first, the third, and the fifth harmonic of the clock in this PCB. But look at this. In this area, I have frequencies that are in 120, 116 megahertz that are coming from this area. In this area, the frequencies, the biggest activity is around 120 megahertz. This area is the area that is related with the buck converter. And you can see exactly, this is the device and the diode that they are switching to go from the 9 input volts to the 5 volts in the power supply. And you can identify that in this area here, let me remove the picture, I have green color. That means that in the cable, I have activity. If this cable is carrying 120 megahertz, and this cable is long enough, you can radiate with the cable to the environment, no? And this radiation is coming from noise that is circulating in common mode, no? Let me show you how is the activity in 3D. If we go to 3D, we can move this activity and we can go in and out in the emissions. So you can see that the peak of the emissions, this peak of emissions is coming from the buck converter here, okay? And especially in the area where I have the main device, no? It's very useful to identify, for example, how is the effect of a ferrite, no? For example, one possibility to minimize the emissions from this cable, the best option obviously is to kill the ringing here, no? If we go to the scope screen and I connect to the DC-DC converter, I connect my probe from the, let me show you, okay? What I am measuring now with a big, obviously this is a big pigtail, but don't worry about this pigtail because the ringing in the transistor is exactly the same without the pigtail, no? Because I have done it previously. So let me show you how is the activity in the time domain in the switching activity of my device, okay? You can see here the switching waveform in the transistor, and you can see this ringing. This ringing in the device is the ringing that is creating the problems, the emissions at VHF and UHF ranges. No? Typically, the solution is to introduce here some kind of a snubber, so the signal is going in this direction, goes up, but this under-damped situation goes to a over-damped situation without the ringing. This is the best solution, but sometimes we don't have this possibility. And one solution, a typical solution in many products, is to introduce some kind of ferrite. No? So you go to the catalog of ferrites and you select the ferrite that introduce impedance. Sorry, you select a ferrite that introduces impedance in the frequency range of interest. So let me scan the board, same board, with the ferrite in place. No? Now I'm going to scan again. And we will be able to change the scales in the idea that we can compare what happened with or without the ferrites. Need some patience. Okay, so while the system is scanning, remember that the idea of this ferrite is this one. Okay, so we have a system like this. We have another system to have the two wires, and the noise is going in common mode. This is what we call common mode. No? This noise for us is a frequency of around 120 megahertz. So the idea is that we go to the manufacturer of the ferrite and is offering one ferrite that is in this way. No? So this is the frequency that is of interest for me. I go for a ferrite. This is another ferrite for the manufacturer. This is another ferrite for the manufacturer. I am interested in this ferrite. Why? Because this ferrite is offering the peak of impedance at the frequency I want to kill. This impedance is, for example, something like 600 ohms. That means that you are introducing here and you are introducing here 600 ohms, but only for the common mode. If you look at this impedance has two parts. The first part is the part of resistive effect. The resistive effect of this ferrite is doing something like this. And the other effect that I am going to plot in pink is this effect that is inductive effect. No? So this is what we call X, reactive effect, and this is what we call resistive effect. Okay? So the impedance is the resistive plus the reactive effect. When we are using ferrite for this application, we want to use the resistive part of the ferrite, so the noise is attenuated. It's not reflected. We don't want reflection. We want to dissipate the noise in the ferrite, so the noise fully disappears. So the scanner is finished. This is the result. And to be able to compare both results, it's very useful to change the scale. No? So this is the previous measurement. Let me see. Let me change the. Sorry. Let me close this. This is the scan now with the ferrite. This is with the ferrite. This is without the ferrite. No. So without the ferrite, let me remove the picture. Okay. Let me remove the overlay. And this is with the ferrite. Remove the overlay. Okay. And here too. And then let me go to the scale. This is without the ferrite. Let me put here from 0.5 to 42, for example. From 0.5 to 42. And now with the ferrite, we go from 0.5 to 42, the same scale. Sorry, 42. Okay, so this is without the ferrite, and this is with the ferrite. Without the ferrite and with the ferrite. You can see that in this area, in the cable, there is no energy going because the effect of the ferrite. Obviously, in this area, the 11 megahertz, 33 megahertz, 50 megahertz is not changed because this is the activity of the digital circuit. And the activity in the buck converter is in the same way because there is no change here. I have not changed the design, so I have the energy here. So if, for example, you have another cable, you have the opportunity to radiate with the other cable. No? Well, this is what I have been trying to show with the EM scanner. So let me go to the EM probe. What happened with the EM probe? The EM probe is useful. First, I am going to change. Let me go here. Let me save this in the disk. Let me say name 1. And let me open another file that is called, for example, this one, okay, this one. And let me change to the new scanner, no? So now I have selected the EM scanner. I'm going to select the EM probe. Okay, and let me show you with the camera where is the application of the camera? Okay, let me see, where is the camera? Okay, here. Okay. Okay, so this is the camera, the other camera, and I'm going to show you the area I am going to scan. Okay, this way. Okay, let me make a show. This is a TV. It's a digital TV. You can see here. You can see here that I have a full product. I have a power supply here. You can see the power supply here. And I have the area where I have digital circuits, where I have radio frequency circuits, where I have connectors, cables. This kind of system is more difficult to scan than a PCB because it's not flat. No? So the idea is to use this robot. The M probe is a product where instead of using several probes in a surface, I am using the arm of a robot where I introduce my near-field probe. So let's take the near-field probe. I take this accessory to introduce the probe in the scanner. Okay, this way. And I connect the output of the probe so the radio frequency can go to the scanner. To the spectrum analyzer. Now, here, I am going to do a spectral spatial scan. No? The first thing to do is to establish the frequency range. For example, 1 megahertz to 80 megahertz in 120 kilohertz bandwidth, resolution bandwidth in the spectrum analyzer. I am not going to measure peaks in this example. If you are interested, we can do it later. And let me show you how is the area I am going to scan. I am going to scan in the camera. I'm going to scan this area. Show you with more detail. Okay, so you can see that this is the area where we have the radio frequency. No, in this area where I have the radio frequency, I'm going to demonstrate how I can use the EM probe to test how effective is the shielding of this area. Okay, so let's go here. Let's put the camera in this position. So let's make an auto zoom so you can see the camera, the probe moving. And then in the settings of the scanner, what you do is to put some kind of overlay. I have used this overlay. It's a picture of this area of the system. And then the probe is in this position actually. But I am going to go from here to here, from here to here, following these selected probes. And then I can select the height I want in the probe. No? In YIC Technologies is developing now a new product, and they will explain you that in the future the height of the probe will be with different height for different probes. But now, this is the way to work. So let's make accept, okay, and then make run. Let me show you the picture, the camera. I hope not to have problems, because the problem with this kind of real demos is that sometimes you can have problems. Things work easier with software. So you can see that the probe is scanning. Okay. System is scanning here. The result is in the screen of the EM viewer, the software, and you can see here how the probe is moving. Okay. You can sweep in some specific frequency range, or you can okay. The scan is finished, so you can see here the result. Okay, this is like previously. You can view the system in 3D. You can identify the areas where you have more activity, or you can see, removing the picture, in what areas you have more energy. No, now I can introduce the shield. No, So let's go to introduce the shield. You can compare different materials. You can compare different designs, the effect of some specific slot or aperture in the design, and you can start again here the scan. No, scan again, and we will obtain a second measurement. Okay. Sometimes you are worried about plastic cover that has been painted with metallic paint, or sometimes you are using some kind of ferrite plate, no, like the ferrite plates that are typical from Booth Electronics, or you are interested in two different materials, two different dimensions in materials, so you can compare with numbers the final product or some specific prototype that is useful to make these measurements. So now we are going to finish. Obviously, to scan this kind of systems is more difficult than with a flat scanner, but the advantage is that the software can work with both of them at the same time. No, this is one, and this is the second one. Let me remove the overlay again, and let me put the same scale. No, in this system, the scale is between 1.9 and let me put here 5.5, 5.5 and 2. So it's easier to remember. From 2 to 5.5. Here in the second, I go from 2 to 5.5. Okay. So this is the difference. Now I don't know why something is wrong. Something is wrong, or I have not connected, because typically the result of this, let me show you one previous example, like this one. Okay, this one, no, this one. This is the result. That typically is what happened. Ah, I know what happened. Sorry. The TV is off. Sorry. Let me switch on the TV. This is signals only from the environment. So I'm going to switch on the TV. Okay, sorry. But I'm going to do this fast. Let me remove these measurements so we cannot have confusion. Let me run again. Oh, sorry, this is not this from this. Run again. I'm going to run again the system. This is the last measurement I am going to do before going to the questions time. And of course, if in the questions time you want some kind of a specific measurement, we can repeat, but we are close to the 1 hour and 30 minutes that we have planned for the event. So you will be able to go for lunch or with your family. Let me spend a couple of minutes. This is the situation where I am measuring with the EM probe, remember, and with the metallic cover on top. This is the opposite. In the previous trial, okay, now is with the cover, and let me now remove the cover, and now I'm going to repeat the measurement. Okay. Sometimes these kind of measurements fail because it's not easy to have problems in demos. But I think today we are lucky. There is no failures with cameras or microphone or with the scanners. So let's. One of the most useful appliances of these scanners is when you need to find where is a frequency that is not part of your design, no? Because if the frequency where you are failing is harmonics of your clock, or the frequency where you have an oscillator, it's not difficult to understand where is the origin. Not easy, but it's not very, very difficult. The problem is when the emissions came from some kind of ringing or from some kind of parasitic oscillation because of the layout of your product. This is the system with the shield. This is without the shield. So let me see the scale. In the scale, here I'm going to go from 2 to 5.5. 5.5. This is the idea. We can see that the areas where I have more activity are in these points. is from 2 to 5.5, and here is, there is no big difference. I don't know why. Oops. There is no big difference. Something is going, no, I have removed it. This is without, and this is with. But there is no the 70 megahertz. No, I don't know. Something is wrong with the circuit, because this circuit has a strong emission around 70 megahertz, and I see that this emission is not here. Both emissions looks like ambient emissions, and in my previous, when I was preparing this demo, in this circuit, there is a strong signal in 70 megahertz that I see now that is not here, okay? So something is wrong with my circuit, sorry. Sorry, but I think we are on time, and I prefer to go to the question and answers, and if someone of you are interested, we can continue later, and I repeat again the measurement so I avoid delay for the people that is not interested specifically in this part. So Joram, you want, we can start with the questions?
Yes, thank you, Art. Just my input. Did you connected the EMP?
Oh no! It's true. This is the question. The question is that I didn't connect the radio frequency output of the EM probe to the spectrum analyzer. Oh.
Yeah. So it's.
Oh, sorry.
Well, I think it's okay, because I think we are on time, so I don't know if we have time to do this again.
Okay.
So yeah, now we can actually accept questions if
yes, I'm going to put the system running without the shield. Then we can start to answer questions, and I will be doing the test while I am answering. Okay. If you want, no? Now the TV is on, the robot is on, and the robot is connected to the spectrum analyzer. So I hope that I don't forget nothing. When I was preparing this experiment in this area, there is a strong peak of 70 megahertz. You can see here the activity I was explaining, no? Here you can see that around 70 megahertz, there is a strong activity. You can see the peak I was explaining before, okay? And it's specifically in this area of the circuit. So this is the result. It's finished. Now let me go to the circuit, and I will introduce the shield. Where is the shield? It's here. So let's go here. Okay, and then we'll repeat the test. It's not very big here. You can see that in this area, there is some activity. Part of this activity is from the environment, and you can see the big peak of 70 megahertz. Obviously, we are in the near field, because at 70 megahertz, that is close to 100 megahertz, the distance between the near and the far field is not so close to the circuit. We are finishing. Okay. And now I'm going to repeat my previous work, changing the scale, no? It's finished. So now I am here. This is without the shield. You can see the big peak at 70 megahertz. Let's go to the scale. In auto scale, let's put here 17 to 40. That is easier to remember. 17 to 40. And this is the sum of the PCB board. And this is the auto scale 17 to 40. We see that there is, okay. So this is without the shield, and this is with the shield. Without the shield and with the shield. And if we are doing this kind of a spectral spatial scan, obviously we can activate the overlay to identify exactly where is the problem, no? The specific area where we have the problem. Okay. and the overlay is here. Okay, okay, okay. So we can remove or we can put where is exactly, and here is the same. We see that the 70 megahertz is around this area here. No? And the other possibility is to go to the user composite view, and when we click here, the system says that in this point, in this cell, the energy is here. But if you go here, there is no 70 megahertz signal. If you go here, you have 70 megahertz signal. So this is the area where I have this specific energy that is going from one side to the other side. Okay, so that's all. I think we were able to review near-field probes, scanners, flat scanners, and the EM probe.
Brilliant. Thank you very much, Art. I'm so glad you did that,
Thank you.
that presentation for us. We can open up now for any questions. If you've got any questions to ask Arturo, you can put them in the chat box, or you can just ask out loud. So if there's any questions at this stage.
No questions?
Okay, so if you do have any questions and you don't want to ask it here, you can either email us at support@yictechnologies.com, and we will send it to Arturo so that he can answer if we're not able to answer. Or Professor, if you just want to put your email down there so people can have a look, and if they want to email you directly. Did you put your email down?
No questions? No.
Okay, thank you very much. We'll end it there. Thank you very much for joining.
Thank you very much to all the people attending. Thank you, Cornel. Thank you, Joram.
Thank you.
Bye-bye.